Welcome back. Our last video introduced factor analysis as a way to recover low-dimensional latent objects from a set of measurements. And in particular, those measurements could be noisy. We also discussed how factor analysis is fundamentally different from principal components analysis, or PCA. And just to review briefly, PCA is a method that creates linear combinations of your original data in ways that maximize the variance with minimal numbers of those linear combinations. Factor analysis, on the other hand, posits a causal model wherein the measurements are determined by a low-dimensional set of latent factors. But so far, we've just written down a model, and we haven't discussed how that model could be identified. So that's the topic of today's video. And identification is obviously important if we're going to do any kind of estimation or hypothesis testing down the line. Let's start by seeing what information is available to us from this system of equations in the factor model. And here I've reproduced the measurement system with the composite error term, and I'm removing the k subscripts that were sort of there to tie it back to PCA. So just right now, assume that theta is k-dimensional, and then lambda is going to be k by j. And we need to make some assumptions before we can move forward with estimating this. We need to normalize the mean of the uniqueness error, or what I would call the idiosyncratic or the measurement error. So we'll just normalize that to be 0 for every single measurement. And then we'll say that the variance covariance matrix of those epsilons is omega. So it's going to be a j by j matrix because epsilon is n by j. And then we're going to assume that there's no covariance in the idiosyncratic component of the measurement. And that's just basically by definition. These wouldn't be uniqueness if there was some covariance between them. And then we'll call sigma squared j the jth diagonal element of this omega matrix. And then we'll also normalize that the mean of the factors are 0. So we're going to assume that we have a two-dimensional factor model so that k equals 2. And then we're also going to have a variance covariance matrix of the factor, which in this case, we're going to denote that as capital sigma sub theta, and that's going to be a 2 by 2 matrix. So if we kind of put these assumptions together, we can just say that the overall mean of the entire error term, this composite error term, is 0 for every single measurement that we have. And the variance is going to be the variance of theta lambda plus the variance of epsilon. And we've also assumed that there's no covariance between these. That wasn't explicit in the previous screen, but that's explicit here. So there's no covariance between those. So we just have the common variance that's shared among the factors. And then there's the unique variances or the idiosyncratic variances that just are a measurement error in our test or whatever. And then this variance covariance matrix of the factor is going to be the variance of each factor. And then we're also going to have a covariance component. So we need to estimate the lambdas, and we need to estimate the elements of capital sigma sub theta, and we need to estimate the diagonal elements of capital omega, the idiosyncratic variance matrix. And the only thing that we have to do that is the variance of u, which is the variance covariance matrix of the residuals of our measurement system. So what does this variance covariance matrix look like? Well, it's going to have j diagonal elements and j times j minus 1 over 2 off diagonal elements that are unique. So if you remember, a variance covariance matrix is symmetric, and so we're basically looking at the diagonal and the lower triangle, and that's how many elements there are that are unique. So we have that many moments in the data, and from that we need to estimate the j diagonal elements of capital omega, the 2 times j elements of lambda. So why is it 2 times j? Well, because we have 2 factors in the model, and each of these j equations for the measurement system has its own lambda. And then there are 3 elements of the variance covariance matrix of the factors. And again, because it's a variance covariance matrix, there's going to be Even though there's 4 elements in that matrix, there's only 3 unique elements. So we have 3 times j plus 3 parameters, but we only have j plus j times j minus 1 over 2 moments in the data. So in general, we need to make some additional assumptions in order to get identification. There's a bunch of different ways that you can do this. I'm going to list some common ways that most people do it, but there's all sorts of ways that you can do it. So first, it's customary to impose that the variance covariance matrix of the factors is diagonal, meaning there's no covariance component. So that gets us one more parameter down in terms of what we're trying to estimate. And the other thing that we need to do is to set the scale of each factor, because the scale is arbitrary. And there's 2 ways we can do this. We can either normalize the variance covariance matrix so that it's the identity matrix, or we can impose that some of the factor loadings are equal to 1 in some of the equations. And then if we make these assumptions, we can achieve identification if 2 times j plus j is less than or equal to j plus j times j minus 1 over 2. So where is this 2j plus j coming from? Well, before we had 2j plus j plus 3, and basically we've knocked out the off-diagonal element of sigma theta and the diagonal elements of sigma theta, or the same number of elements of lambda, depending on how we chose to do this one. So we had 3j plus 3, now we're down to 3j. I'm writing it as 2j plus j just to emphasize that we have factor loadings that we need to estimate, and we have the idiosyncratic variances that we need to estimate. So this is our identification inequality condition, and basically, in general, we need j to be more than or equal to 5 measurements. So that's necessary, but not sufficient for identification. And then, aside from identification, we may want to just be able to interpret the model. And for model interpretability, we may need to impose further restrictions on the factor loadings in particular. So if we suppose that we have 6 measurements, we want to estimate 2 factors, or allow for 2 factors to have determined those 6 measurements. And suppose that we have 3 cognitive test scores and 3 personality test scores. So in this case, if it's a personality test, then it should not be a function of the cognitive factor. So basically what we're going to do is we're going to restrict those factor loadings, those elements of lambda, to be 0 for the measures that are clearly not a function of those factors. So this is just basically saying, if I am giving a personality test, I'm not going to suppose that there could be any contribution of the cognitive skill of the person to that answer to the personality test question. So if we only had cognitive test scores, then we shouldn't try to estimate a factor that has to do with non-cognitive skills. And if we do have sufficient overlap in some of the measurements, it could be possible to identify covariances between the factors, but that's something that's problem specific and not something that we could do generally. So the idea there would be, maybe my GPA is a function of both my motivation as a student and my ability as a student. And so I could use the GPA as being a measure of both of those factors, and that could pin down the covariance between them. But I would need like a lot of other measurements like GPA that would have that overlapping to really be able to pin down that covariance. All right, well, that was identification of the factor model. In the next video, we'll talk about how we actually estimate this using data. And what we'll see is that there's a lot of resemblance between how we would estimate this factor model and how we've estimated the mixed logit model or other models that incorporate preference heterogeneity. So I hope to see you in the next video, and thanks for joining this one.